Hello viewers, welcome to another exciting video on current electricity. This is the second video on current electricity and we will continue from where we ended. Now in our previous video, we were looking at terms used in the study of current electricity. We were looking at terms used in the study of current electricity. As a brief recap of some of the terms that we looked at in the previous video, we looked at electric charge. We looked at electric charge and we defined charge as a property that an elementary particle has that enables it to experience a force when it is placed in an electric or magnetic field. So it's a property that an elementary particle has that enables it to experience a force when it is placed in an electric or magnetic field. Then second, we looked at electric current. And we defined current as the rate of flow of charge. And thirdly, we looked at potential difference, PD, and we defined potential difference as the work done in moving a 1 coulomb charge across a circuit component. Then fourth, we looked at electromotive force, EMF, and we defined EMF as the work done in moving a 1 coulomb charge across or around a closed circuit. Okay, we also looked at resistance, electrical resistance, and we defined electrical resistance as the opposition to the flow of current. And under electrical resistance, we further went on to look at the factors that affect electrical resistance, and the factors were 1, temperature, 2, length of the conductor, third, we had cross-sectional area. Okay, we had temperature, length, and cross-sectional area. So we ended on these. However, today will be the continuity. It will be the continuity of where we ended. So in this particular video, we are starting to look at resistors. So we're looking at resistors. So we will look at resistors, and the question that obviously needs to be answered is, what is a resistor? A resistor is a circuit component that offers or that opposes the flow of current. So a resistor is a circuit component that opposes the flow of electrical current. A resistor may be anything. It may be a wire, it can be a lamp, it can be anything. Okay, however, we have special devices that actually are specifically meant to oppose the flow of electrical current, and these are resistors, and they are actually denoted. So the symbol of a resistor in a circuit component is so a resistor may be denoted by the following symbols. Okay, so the first symbol will be a terminal, okay, a rectangular box, another terminal. The other symbol will so this is a resistor. So R is the magnitude or the size of the resistor, and also so a resistor is usually denoted like that. So there will be cases like, let's say they give us this kind of thing where they put 3 ohms. It means that the size of this resistor is 3 ohms. Okay, so the size of this resistor is 3 ohms. So this is how we are going to actually denote our resistors. All right, having looked at the symbols, we can now look at the connection of resistors. So connection. How can resistors be connected in a series? So they can be connected in either series or parallel. So there are 2 ways in which resistors may be connected. So they can either be connected in series or they can be connected in parallel. So the first thing we are going to look at is resistors connected in series. So resistors connected in series. Okay. So we've already come across this term series when we were looking at how an ammeter is supposed to be connected. So so in an ammeter, we said that when the 2 terminals of the ammeter are connected to 2 different circuit components, then the ammeter is connected in series. So also, when a resistor is connected in series, it means the 2 terminals of a resistor are connected to 2 different circuit components. So this is when the 2 terminals of a resistor is connected to 2 different circuit components. Okay, so this is when the 2 terminals of a resistor are, this is R, not is. So when the 2 terminals are connected to 2 different circuit components. How does this look like? All right, so if we have one resistor here, okay, and we need to connect this resistor to another resistor, which is another circuit component, it means that we are going to have our second resistor there. So this is our resistor 1, this is our resistor 2. So for us to connect these 2 together in series, it means that this terminal of this resistor is going to be connected to that. Okay, and if we have a cell somewhere there which also has terminals, so for us to connect this, it means we are going to get this terminal and we're going to connect it to this terminal of this resistor, and we're going to get this terminal and connect it to that terminal, and the same happens to that. So when resistors are connected like this, they are in series. So this is a series connection of resistors. So in a much cleaner illustration, we can safely now just do this, just showing the resistors themselves. This is our R1, resistor 1, and this is our resistor 2. So these two resistors are connected in a series. So this is a series connection. So you may have as many resistors as you want connected in series. There is no limitation that only two resistors. If we wanted, we can add another resistor so that we have three resistors in series. If we want, we can have four resistors. If we want, we can have an infinite number of resistors connected in series, if we can ever actually have those many number of resistors. Okay, now for resistors connected in a series, we can actually find the total resistance of these resistors. What is the total resistance that your resistors that are connected in series are offering? So total resistance. Okay, I actually like to actually denote my total resistance with yeah, I know resistance is R, but I like to put a subscript T to show that this is the total resistance. So total resistance RT, which is R total. So for resistors in series, the total resistance is the sum of resistance of each resistor. So this is the sum of the resistance of each resistor. So when we say sum, it means it is when we add and what we find the total of the addition of all the resistance of each resistor in that series connection, then we will have the total resistance of the resistors connected in series. So we can actually just do a quick example. Okay, example. So study the circuit. Study the circuit shown below. So what is the total? What is the total resistance of the circuit? So what is the total resistance of the circuit? What is the total resistance of the circuit? So this particular circuit only has two resistors, which is 1 and 2. So we have two resistors. So in our solution, we can actually write down the data. If so, we have the resistance of the first resistor. So any of the two can be the first resistor. So in our particular case, the first resistor has a resistance of 3. So we can say R1 is equal to 3 ohms, R2 is equal to 4 ohms. So R1 has gotten, so we only have 2 resistors. So our formula, since it is the sum, okay, since it is the sum, the general formula for resistors in series is R total is equal to R1 plus R2 plus so on and so forth plus Rn, which is the nth resistor. However, we cannot go on and write this formula like this. Okay, in our case we only have 2 resistors, so we will only write R1 and R2. If there were 3 resistors, we would have had R1, R2 and R3. So our formula, we will actually have R total is equal to R1 plus R2 for 2 resistors. So this is going to be 3 plus 4, and 3 plus 4 is equal to 7. 7 what? 7 ohms. Units are very important. Forget the units, forget the mark. All right, so this is how we find maybe another quick example. Okay, another quick example. Okay, for this one it will just be find the total resistance of the following. Find the total resistance of the following: A, so we have that as A. Okay, so we have that as A, and B we will have so that is A and B. So for A, so solution for A, so A, how many resistors do we have? We have 1, 2, 3. So we've got 3 resistors. So we're going to say the total resistance is equal to R1 plus R2 plus R3. So R1 is 2, R2 4, R3 6. So we are going to say 2 plus 4 plus 6. So 2 plus 4 is 6. 6 plus 6 is 12. So this is going to be 12 ohms. So that is the total resistance for A. For B, we only have 2 resistors, which is 1 and 2. So our formula will be the total resistance is equal to R1 plus R2. So in this particular case, we are going to have 10 plus 16. This is going to be 10 plus 16 is 26 ohms. So that is the total resistance. All right, now there are things examiners are always trying to find out from a candidate. There are always things that examiners will always try to find out from a candidate, and these are very important. Take note. So points to note. Points to note on resistors in series. Points to note on resistors in series. 1. The first one is that the current flowing through each resistor is the same. Okay, the current flowing through each resistor is the same. Okay, the current flowing through each resistor is the same. Second, okay, the second point is that the potential difference through each resistor is not the same. The potential difference through each resistor is not the same, or may not be the same. However, the sum of potential differences across resistors in series is equal to the EMF. So the potential difference across each resistor is not the same. Now, I said is not or may not. If the two resistors have got equal resistance, the potential difference will be the same. But if the resistors have different values of resistance, then the potential difference is different. Okay? However, the sum of these is different. Now, to better understand these two points that we've written, allow me to illustrate using a diagram. So in my diagram, I will have 4 towns. We will have Lusaka, okay? Lusaka. We will have Lusaka. We will have let's say Kabwe. We will have Kapiri, and we will have Ndola as our last town. Now, all these towns are connected by a road network. So they are connected by a road. So for you to move from Lusaka to Ndola, okay, you need to pass through Kabwe, Kapiri. Then you reach Ndola. Now, there is a bakery in Lusaka. There is a bakery in Lusaka. And this bakery, every day, 4 trucks leave Lusaka carrying bread to sell. And these 4 trucks arrive in Ndola with no bread. Okay? The trucks arrive in Ndola with no bread. They need to reach Ndola, refuel, and go back to Lusaka. And the following day, the journey starts again. Now, the question is, how many trucks will pass through Kabwe every day carrying bread? Okay, so if 4 trucks leave Lusaka heading for Ndola, it means that 4 trucks will pass through Kabwe. The same 4 trucks will pass through Kapiri. The same 4 trucks will arrive in Ndola. Are we together? However, if the 4 trucks, each truck, okay, if the 4 trucks carry a total of 4,000 loaves, okay, they carry 4,000 loaves of bread. They carry 4,000 loaves of bread. And no bread, there is zero bread that arrives in Ndola. It means that the 4,000 loaves of bread have been sold in Kabwe and also in what? Kapiri. So the 4,000 loaves will have been sold in Kawe and also in what? Kapiri. Now the question is, will the 4 trucks sell the same amount of bread in Kawe and also in Kapiri? The answer is no. The amount of bread sold in Kawe may be different from the number of loaves of bread sold in Kapiri. And this is because the number of loaves sold in each town depends on the demand of the commodity in each given town. So if the population of Kawe is bigger than the population of Kapiri, it means that more loaves will be sold in Kawe than in Kapiri. So the number of loaves of bread will be different. Now let's look at that. So demand actually dictates how much bread is sold in each and every town. Okay? Now let's take it as if we have 2 resistors. So the market is the resistors. So imagine, let's take it as if we have 2 resistors with the same path, with the same path. So it means that whatever is carrying the loaves, we'll take it as if that is current. So we'll take the trucks to be current. Okay? So electric current coming from Lusaka, which is the starting point, okay? The same amount of current will pass through resistor 1, okay? The same amount of current will pass through resistor 2 and up to the end, okay? This is start, okay? So current is the same, just as the number of tracks. The number of tracks that will pass through resistor 1 is the same as the number of tracks passing through resistor 2, is the same as those that will arrive at the end. However, because opposition is more like demand, so the number of loaves sold here, which will be now the potential difference. So this is like the potential difference. So potential difference across resistor 1 will be V1. So the potential difference across resistor 1 will be V1. It will not be the same as the potential difference across resistor 2, which will be V2. However, okay, the V will be equal to the total potential difference across the two will be equal to V1 plus V2. So the potential difference is not the same, but the current is the same. All right. Let's move on. So that is about resistors in series. The current flowing through resistors is the same. However, the potential difference is not the same. Are we together? All right. Let's turn our attention now to resistors in parallel. So parallel connection of resistors. So resistors in parallel. Okay. Now, when are resistors connected in parallel? So resistors are connected in parallel when both terminals of a resistor are connected to different terminals of the same the same circuit component. Okay, so when different terminals of one resistor are connected to different terminals of the same circuit component. Now, what do I mean? So, if I have a lamp there, okay, these are the terminals of a lamp, okay. Now, if I have a resistor, this is my resistor, and these are the terminals of the resistor. If these terminals of my resistor are connected to the terminals, to this terminal of the lamp, and also this other one is connected to this terminal of the lamp, then these are parallel, just like parallel lines. Parallel lines move like that. So we have a component here and another component there. So these are in parallel. So this is our resistor, that is our lamp. So resistors may also be connected in parallel. So how can we denote resistors that are connected in parallel? So we may have a resistor there, okay, and we may have another resistor there, okay, and it goes out like that. This same arrangement may also be drawn like this. Where this is R1, this is R2, this will be R1, and this will be R2. So this and A and B are just one and the same. So the terminals of this resistor, this terminal is connected to the other terminal of the other resistor, and this one is connected to the other terminal of the same resistor on top. So we may have a number of resistors connected in parallel. However, the total resistance the total resistance for resistors in parallel is different in calculation. Okay, so the total, how do we find the total resistance of resistors connected in parallel? So the inverse of the total resistance is equal to the sum of the inverse of the resistance of each resistor. So the inverse of the total resistance, the inverse of the total resistance is equal to the sum of the inverse of the resistance of each resistor. It sounds a bit complicated, but it is relatively easy. So that is mathematics in English. Okay. However, mathematics in mathematics, the formula is just going to be 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over Rn, which is the resistance of the nth resistor, because we may have a given number of resistors that are connected in parallel. So how do we use this? So Example. Find the total resistance of the following. A. Then B. So those two. So A and B. So let's start with our solution. Okay. So for A, how many resistors do we have? We have 1, 2, 3 resistors. So we've got 3 resistors. So we are going to say 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So then we can now start substituting. So if R1 is 2, R2 is 3, R3 is 4. So we are going to say 1 over 2 plus 1 over 3 plus 1 over 4. Okay, so since these are fractions, what we're going to say is we look for the lowest common denominator. So the lowest common denominator, 2, 3, and 4 is 12. Okay, so 2 into 12 is 6. 6 times 1, so it's 6, plus 3 into 12 is 4. 4 times 1 is 4. Okay, plus 4 into 12 is 3. 3 times 1 is 3. So we have that. Then we are going to add 6 plus 4 is 10. 10 plus 3 is 13. So we are going to have 13 over 12. Now, remember that this is 1 over R total. 1 over R total. Okay? So it means even here it's 1 over R total. Here we are looking for R total. We are not looking for 1 over R total. So we are going to cross multiply. So we are going to have R total times 13 is equal to 1 times 12. So this will be 13 R total is equal to 12. Okay? Then we are now going to have to divide both sides by 13. Divide by 13. So 13 there goes. So we remain with that. So our total resistance is equal to 12 divided by 13. What is 12 divided by 13? 12 divided by 13 is equal to 0.92. 0.92. So our total is equal to 0.92 ohms. So this is the total resistance for A. This is the total resistance for A. All right. Then we go to B. B. Okay. Let's get back here. B, we've got 1, 2. We've got 2 resistors. 1, 2. and we've got 3 and 4 ohms. So we've got two resistors, 3 and 4 ohms. So we're going to say 1 over the total resistance is equal to 1 over R1 plus 1 over R2. Then we are going to say that 1 over R total is equal to 1 over 3 plus 1 over 4. Okay, we look for the lowest common denominator, which is going to be 12. Okay, again 12. So 3 into 12 is 4 times 1 is 4 plus 4 into 12 is 3 times 1 is 3. So this 1 over R total is equal to 4 plus 3, 7 over 12. So 7 over 12. Again, we are looking for R total, so we're going to cross what? Multiply, which will be R total multiplied by 7 is equal to 1 multiplied by 12. So this is going to be 7 R total is equal to 12. So we divide both sides by 7. We cancel the 7 there. So R total is equal to 12 divided by 7. 12 divided by 7. So 12 divided by 7, which is 1.71. 1.71. So 1.71 ohms. So the total resistance for B is 1.71. However, for two resistors, not only for two resistors, you can have an alternative formula just for two. So just take note, don't use it if there are 3 resistors in parallel. Just for 2 resistors, in parallel, okay, you may use this formula. R total is equal to R1 times R2 over R1 plus R2. This will get the job done. So in our case, we actually have R total is equal to, we have 3 multiplied by 4 divided by 3 plus 4. So 3 times 4 is 12 over 3 plus 4 is 7, which gives us 1.71 ohms. So this formula only works. This formula only works for 2 resistors. Do not get 3 resistors and start saying R total is equal to R1, R2, R3. It doesn't work. It doesn't work. Okay, so this formula is only restricted to 2 resistors, not 3, not 4. You need to go the long way if you have more than 2 resistors. All right, just as we did for resistors in series, we now look at what points should be noted about resistors in parallel. So points to note. All right, points to note. The first point is that the current flowing through each resistor in parallel is not the same. So the current flowing through each resistor is not the same. The current flowing through each resistor is not the same. Secondly, The PD across each resistor is the same. The PD, the potential difference across each resistor, is the same. Okay, so the current flowing through each resistor is not the same, okay, but the PD across each resistor is the same. The PD across each resistor is the same. These are the two most important points to take note when you are dealing with resistors in parallel. All right, we end here in this particular video. In the next video, we will look at the relationship between current and potential, current, resistance and potential difference, and this will be on Ohm's law. Thank you very much. If you are a new viewer to this channel, please don't forget to subscribe and hit the notification button.